Hi, I'm Ryan Ulf. I'm a graduate student in physics at UC Berkeley. I work in a field called atomic, molecular, and optical physics. It's kind of a hybrid field with ancient roots. So atomic physics began kind of as the study of atoms. And the first thing people did was, well, first of all, the Greeks thought maybe there was something called an atom, which was some indivisible unit of matter. It turns out that there are such things that had been called atoms, although they're not indivisible, as nuclear physicists will tell you. Atomic physics is not the same as nuclear physics. The nucleus is a part of the atom, and it actually has its own structure that looks a lot like an atom. Chemists and physicists realized that there were these different types of matter, different elements, they make the periodic table, and that they have some kind of standard properties. And atomic physicists got their start kind of studying these properties of atoms. And one way in which these properties are manifest is people realize that if you look at the spectrum of light of the sun, so the sun gives out radiation in the form of light, and this light has lots of different colors. And if you look at the colors that the sun puts out, there's a really huge range of colors. Like you can put something red in front of like some sunlight and it'll look red, so you know that there's red in the sun. You can put something green in the sunlight, there's green in the sun. If you ever looked at something green under a green light, it looks green. If you put something red under a green light, it looks black. That means there's no red in the green light. And you look at sunlight on a prism, you'll see like this whole rainbow of colors, just like you see in the sky, a rainbow that breaks the sun's kind of light spectrum apart. You'll see, if you have a really good resolution, that there's some lines missing. And this is kind of the beginning of atomic physics. People wanted to know, why are there lines missing? It turns out that this is because the sun is made of hydrogen, and this hydrogen absorbs just very narrow bands of light. So if I have a bunch of hydrogen and I shine just white light to the hydrogen, almost everything gets through except for just these little narrow bits of light. And the question was, why these narrow bits of light? So we learned to understand hydrogen atoms and lots of other atoms and the properties of atoms and how they interact, and a whole range of things beyond just what this hydrogen atom, which is kind of the foundations of quantum mechanics. And atomic physics has evolved from measuring the properties of atoms to using the properties of atoms to measure and understand other bits of the world. And one important aspect of this is that these atoms, every atom of the same type, has the same properties here as it does everywhere in the universe. And it has the same properties here as it does everywhere on Earth. And that means that it makes a really fantastic ruler for measuring things. And one of the things that it makes a really great ruler for measuring is time. So you've probably heard of things called atomic clocks. Atomic clocks use this very precise structure of the atom to determine to get a frequency. So light waves and other forms of electromagnetic radiation are characterized by a frequency. So when I was saying that certain lines were missing, I was saying that light with certain frequencies is interacting with the hydrogen atom. And the precision to which we can measure these frequencies using the tools that atomic physicists have developed over the years is so good that these are the quantities. The frequencies of these atomic, we call them transitions, are known so well that they're actually the best measured quantities ever. Unless there's an alien race out there that has done it better with some other system. So these are extremely robust and extremely precisely known physical rulers. Now that we can measure time extremely well, or we can measure frequency very well by comparing it to an atomic clock, anything that you can relate to a time is something that you can now measure very well. For example, you say that you have a satellite. You have two satellites, and each satellite is sending a message, and they're going to send this message at exactly the same time, and they can do this because they have atomic clocks that are very precise. And each one of these pulses is going to be sent at the same time, and you know at what time these two satellites are going to send this pulse. Because of the speed of light is finite. Depending on your relative distance from these two satellites, you'll receive the message from one first and before the other. And what that means now is that you know that you're closer to one of these satellites than the other. And if you can measure the time that the pulses arrive extremely accurately, because maybe you have something that's referenced to an atomic clock, now you know exactly what the relative distance to between these two satellites and you is. Which means that actually if you just do a little bit of math, which is extremely easy for a computer to do, you can maybe look at a few more satellites and the signals that they're sending. Using these very precise clocks, you can actually determine your position. And this is how GPS works. GPS relies on extremely accurate clocks on satellites, sending signals at regular intervals, and you using an extremely accurate clock in your cell phone to determine position. And so this is just one kind of very practical thing that atomic clocks have enabled.